Next up, matrix multiplication. So we are going to see how well this works. Normally when I teach this in class, I've got things up on the board and I'm gesturing and I don't know how well this is gonna work. We're gonna try it. How many people are comfortable with multiplying matrices together? Okay, hopefully for the most of you who are not, and that is fine because this is not a prerequisite for this class, hopefully for those of you who are not, this will work out okay. Matrix multiplication. First of all, if I'm going to take A times B, if A is an M by N matrix, then I need B to be an N by something matrix. It doesn't matter what the something is, but the number of columns in A has to equal the number of rows in B. We'll see why in just a minute. And then my result is a matrix that is M by P. M rows, P columns. Okay, the way that we do this is, let's say that this is C sub ij. All right, that's my shorthand notation. I goes from 1 to M because there are M rows. J goes from 1 to P because there are P columns in my new matrix that I've made, okay? And this is where C sub ij is row, hang on a minute, I of A times column J of B added together. Row I of A, maybe we'll put that in parentheses, row I of A times column J of B, and then that is added together. Easiest way to do this is with an example. So let's do an example. And again, if you've taken linear algebra, if you are comfortable with this, you can kind of tune me out, work the example on your own. And if you haven't, I'll try to do as much circling as I possibly can. So reading across, A is 2, 3, negative 1, 4, negative 2, 6. This is where I really miss having you in class because I can't ask for an interactive example. It's not great. Sorry, you're stuck with mine. B, then A has 3 columns, so B has to have 3 rows in order for this to work out, right? So let's do B 1, 2, 3, 4, 0, negative 1, 2, negative 1, 5. I read down that time instead of across, sorry. B is going to be 1, 4, 2, reading across 1, 4, 2, 2, 0, negative 1, 3, negative 1, 5. So A times B is going to be a 2 by 3 matrix. Do we see why? A is 2 by 3, B is 3 by 3. If I take the outside dimensions and I squish them together, A is going to be a 2 by 3 matrix. All right, so here we go. A times B. First up, row 1, column 1. That's going to be row 1 times A. So 2, 3, negative 1. Row 1 times A, or row 1 from A, column 1 from B. So 1, 2, 3. Multiply and add. Row 1 from A, column 1 from B, multiply and add. That's your rule. That's how this works out. Again, normally I would be going across and down, and you can't see that, and it's unfortunate, and I can't gesture at the board, and I miss my classroom. Okay, next up, I have row 1, column 2. So this is row 1 from A, 2, 3, negative 1. Column 2 from B, 4, 0, negative 1, multiply and add. row 1 from A, column 2 from B, multiply and add. Last one across, row 1, column 3, row 1 from A, column 3 from B, multiply and add. Okay, I'll put my screen back up in a minute, I promise. But people who haven't had linear algebra, basic idea, making sense? Multiplying matrices together, people who haven't had linear algebra, yes, going, yes, good, okay. All right, I'm gonna stop talking. I am going to share my screen again and you can finish out for me, please. So I'm just gonna start writing stuff in here without talking. I think that's gonna be better. Go ahead, write some stuff and see if you can get the rest of these. So there's 3 more. And I really don't care what the answer is. I trust that you can simplify when you multiply stuff out. Okay, row 2, column 1. 4 times 1 plus -2 times 2 plus 6 times 3. Row 2, column 2. 4 times 4 plus -2 times 0 plus 6 times -1. Row 2, column 3. 4 times 2 plus -2 times -1 plus 6 times 5. Give me a thumbs up. Tell me we're good. Making sense there. Everybody's happy. Excellent. You can now do the first week of linear algebra. Okay, so properties of matrices part 2. More properties of matrices. More properties of matrices. More properties of matrices. First of all, A times B times C is equal to A times B times C. As long as everything is the right size. So I need to make sure that everything I have here is the right size. A times B times C is A times B times C. Here's the problem. I don't have separate symbols for matrix multiplication and scalar multiplication, so we're just gonna assume we know which one we're doing. So this, even though I have a dot that I used before, I'm assuming that we know that this is matrix multiplication. Matrix multiplication is associative. All right, and then I can also do A times B plus C equals A times B plus A times C. And so this is going to be matrix multiplication distributes over scale or matrix addition. Matrix multiplication distributes over matrix addition. These look the same as the symbols that I had last time, but we're gonna assume we know what you're working with. So non-property. Don't do this. People who have had me for linear algebra know I get super crabby about this. A times B is not equal to B times A. I'm gonna say in general. We can come up with some specific times when A times B and B times A are equal. We can absolutely do that. But in general, these two are not. So in linear algebra, if we were proving that these two were not equal, we'd need to find a specific counterexample. Specific counterexample that would tell us that these two are not equal. Matrix multiplication is not commutative in general. There are special examples where matrices will commute, but in general, matrix multiplication is not commutative. Okay, we've got a special type of matrix called a transpose. So the transpose of A My notation is A with a superscript of a capital T. Sometimes books use lowercase t as well. Either way, this is A with the rows and columns flipped. A with the rows and columns flipped. So instead of reading across, you read down if you want to make A transpose. A with the rows and columns flipped. Easy, no big deal. All right, pausing again. How we doing? Anything for questions? Doing good? So far so good? Anybody, anything? No questions? We're good? Okay, all right, cool. Inverse matrices, and then we will get into stuff we've seen a little bit, but not entirely. Inverse matrices. First, we need a definition. The identity matrix is denoted by capital I. It is going to be an n by n matrix. So it is always square. A matrix is square if it has the same number of rows and columns. Okay, so this is a square matrix. It is going to have ones on what's called the main diagonal, ones on the main diagonal, and then it's going to have zeros everywhere else. So I'm going to draw some big gigantic zeros and assume that you know what I mean. Ones on the main diagonal and zeros everywhere else. The reason that this is the identity matrix is because A times I is equal to A. If we were in linear algebra, we would prove that as well. We are not proving things in here. So that is why this is called the identity matrix. And then we can talk about inverses. So if I do a definition, let A be an n by n matrix. The inverse of A is the matrix A inverse, so that A times A inverse is equal to the identity matrix, and A inverse times A is equal to the identity matrix. That's a subscript or superscript of -1, and that didn't come out super clearly, sorry. So A inverse, exponent of -1. A inverse, so that A times A inverse is equal to I, and A inverse times A equals I. I need both of those equations because matrix multiplication is not always commutative, right? So I need both of those equations because matrix multiplication is not always commutative. A inverse doesn't always exist. So here's a cool handy dandy theorem that we absolutely prove in linear algebra. This one's fun. A inverse exists if and only if, remember that's to both directions, if and only if the determinant of A is not equal to 0. And we've talked about how to do determinants of both 2 by 2 and 3 by 3 matrices, right? We're good at those. So A inverse exists if and only if the determinant of A is not equal to 0. If A inverse exists, this might be new terminology for people. I'm not sure if we talk about this in linear algebra. If A inverse exists, A is a non-singular matrix. Non-singular. If A inverse exists, A is a non-singular matrix. If A inverse does not exist, A is what's called a singular matrix. Non-singular equals non-invertible. Yes, non-singular is no. So they're opposites. Non-singular means invertible. Singular means non-invertible. Yeah, opposites, totally opposites. So this would be non-singular matrix or invertible matrix. Yep. And singular matrix or non-invertible. Non-invertible, that's not how you spell that. Non-invertible matrix. Singular has to do with like a point of singularity. A point of singularity is where bad things happen on a graph. So that's what's going on here with singularity. Okay, if A is a 2 by 2 matrix, then we have a really nice formula for finding A inverse. Bigger ones, not so much, but 2 by 2 matrices are really easy to find the inverse of. So inverses of 2 by 2 matrices. This is absolutely something that you might want to put on your cheat sheet. If A is equal to AB, CD, then A inverse is, I wish we were in class because I would ask everybody who's taken linear algebra what the inverse is and we'd see how well you remember what I taught you. Probably me, because no one else has taught it for a while. How well you remember what I taught you. I'm just going to give it to you. This is sad and disappointing. 1 over AD minus BC. So 1 over, remember AD minus BC is the determinant of a 2 by 2 matrix, right? 1 over AD minus BC. You flip or interchange the D and the A, so those change places. And then the other entries, you put a negative out in front. So reading across D, negative B, negative C, A, reading across. If we were in linear algebra, here's the theme of today. If we were in linear algebra, we would prove this. We would prove that A times A inverse is equal to the identity matrix. So if that sounds interesting to you, take linear algebra. If it doesn't, you have to take it anyway if you're a math major, sorry. But that's where this next step would be. All right, do I need to do an example? Let me stop sharing my screen. People who haven't had linear algebra before, do I need to do an example of finding an inverse of a 2 by 2 matrix, or are we good? Anybody desperately want to see an example of finding a 2 by 2 matrix inverse? Anybody, anybody? Nobody is jumping up and down and say, I desperately want to see an example of a 2 by 2 inverse. Okay, we're gonna go with no.